In this lecture, we'll cover a couple of additional examples that are a bit more sophisticated. The first example involves the simulated weathering of granite along a one-dimensional column, where we'll look at how to handle a number of equilibrium mineral phases all at the same time, and also have our first introduction to reactive transport, albeit in a simple way. The second example involves an introduction to modeling reaction kinetics, in this case the dissolution rate of pyrite as influenced by specific surface area, oxygen concentration, and pH. So to start out with, for our first example, granites and other types of igneous rocks are, of course, formed from magmas. They contain mineral phases that are not all that chemically stable under near-surface conditions, particularly when exposed to mildly acidic water that could be generated, for example, by biogenic carbon dioxide in the overlying soil profile. As a result, these minerals slowly weather away into more stable mineral assemblages. Think clay minerals here. This can take a very long time, of course. An equilibrium model is instructive in demonstrating how the whole mineral assemblage is transformed. Again, you can think of the geochemical model figuring this out on its own from its thermodynamics, so the user can avoid having to hardwire in all of the potential reactions that could be envisioned. So let's set up a conceptual model for the weathering of a section of granite, perhaps a column associated with a fracture, if you like. This would include dilute water containing dissolved carbon dioxide entering the column at one end. As the percolation front advances, unstable minerals will dissolve. The weathering products from these dissolution reactions may precipitate in place. In the meantime, displaced ions may be flushed further into the column. As this whole process proceeds, we would expect that the column is gradually transformed from one end to the other. An issue to keep in mind is how Freak-C actually transforms a primary mineral into a secondary mineral weathering product. A geologist might think about a feldspar mineral, for example, transforming in place into a clay mineral. Freak-C, on the other hand, bases its calculations on solution chemistry equilibrium considerations. It really solves the bottom two equations shown on this slide simultaneously, along with many others. So for an equilibrium model, all minerals dissolve or precipitate via the solution. This is a very subtle distinction, but just something to keep in mind. Again, Freak-C is using thermodynamic considerations to make choices about which mineral phases are converted into which. So, as far as the granite is concerned, think of a sample of granite and its mineralogical composition. You'd expect to find some feldspars, such as potassium feldspar and sodium feldspar, for example, along with quartz and perhaps a little bit of biotite mica. Other minerals could be present, of course, but let's start with this set for now. What is a reasonable equilibrium composition of a groundwater that is in contact with this granite? Well, the answer could be variable, depending on the starting composition of that background groundwater, as well as the precise composition of the granite. What if calcium feldspar is added in as an example? Without careful consideration, the imposition of an equilibrium condition can lead to strange and sort of unrealistic water compositions that may not be useful for subsequent modeling of weathering reactions. So one approach that I've used is to employ a reaction block to simply throw in a bunch of possible mineral phases into what starts out as a very simple dilute sodium chloride water. As more and more reactants are added, a large set of posited granite mineral phases and possible weathering products are allowed to react with the resultant water, precipitating and in some cases redissolving again. So here we see the results of simply trying to set up this problem by this simulated experiment with the positive groundwater composition and its evolution shown on the left and the makeup of the granite shown on the right. The end result is a mildly alkaline water composition with reasonable amounts of major dissolved constituents that one might expect in a groundwater sample. The end product of the mineral assemblage is, in my view, a very believable granite composition, along with some smectite clay as a weathering product. The pie chart at the bottom shows a starting composition for our granite weathering scenario with mineral proportions shown with respect to mass per unit volume. Note that the starting proportions of all the minerals can be set by the user, since all minerals in the model are in equilibrium with the solution, and so the starting amount for each mineral doesn't really matter in a sense. Now we're going to take a block of this granite and divide it up into 30 cells, all initially identical to one another. This distribution is defined using equilibrium phases 1 through 30 with corresponding solutions 1 through 30. The advection keyword tells freq-c that this is simply a plug flow transport simulation consisting of 7,500 shifts. A shift refers to moving the solution associated with each cell over one adjacent cell and then re-equilibrating. A fresh composition, solution 0, enters at the upstream end, or cell 1. Here are the simulated mineralogy results after 7,500 shifts, or 250 pore volumes. I assumed a very high porosity, approaching 50% here, to mimic a broken up fracture zone at the land surface. The fresh granite is replaced by a mixture of clay, quartz, secondary silica, kaolinite, and iron oxide. The latter coming from the breakdown of the biotite. These results, to me, seem pretty intuitive, but keep in mind this is just a demo. It's worth noting that the primary granite mineral assemblage is not completely replaced with weathering products across the entire column, even after 250 pore volumes have passed through, again, assuming equilibrium conditions. This indicates that the net amount of mass transfer required to reach equilibrium between the solution and the mineral phases is rather small. If reaction kinetics were included in this model, the unweathered granite would persist over much longer timescales. So all of this sort of helps to partially explain the slowness of the chemical weathering process. So this is what the corresponding equilibrium soil water chemistry looks like after 250 pore volumes, again, maintaining local equilibrium with the mineral phases we saw in the previous slide. The pH is elevated in the unweathered portion of the granite, while various ions either increase or decrease in concentration along the column. Although these results represent ideal equilibrium values, the modeled concentrations could be helpful with a real field study. Significant departures from these numbers could, for example, indicate that one or more dissolution or precipitation reactions is kinetically very limited, and that the overall conceptual model might require some revision. So, switching gears here to the topic of modeling reaction kinetics is deliberate on my part. Everything we've modeled up to this point has assumed instantaneous equilibrium between all species and phases in the simulation. As we've seen, particularly with the granite weathering example, this can suffice in generating semi-quantitative results that may make sense as a cartoon, but the associated timescale is poorly constrained. And in some situations, let's say redox reactions occurring over short timescales, the assumption of equilibrium may be a very poor one, at least in regard to certain details. So freq-c provides a very flexible facility for modeling kinetic reactions. A basic-like scripting language is included that allows you to write rate laws that depend on model variables such as solution composition, mineral mass, and so forth in any way you'd like. This is a double-edged sword, though, in some ways. In principle, including a powerful kinetics modeling capability provides freq-c with enormous modeling power. You could simulate almost any process, and you could do it convincingly well if you had the data. This becomes a problem when off-the-shelf kinetic models or data are lacking. So do you try to invent your own rate law by fitting a model to a data set somehow? What if there are many kinetically limited reactions in your problem? Setting up and interpreting the simulation could quickly become unwieldy. In addition, adding kinetics to a freq-c simulation can greatly slow the execution time. Given all this, it's difficult to provide a comprehensive set of examples using and demonstrating freq-c's kinetic modeling capabilities. The universe of potential application demonstrations is simply too vast. Instead, to me, it makes sense to split the kinetics modeling tools into two broad categories with an example from each. One would be the dissolution of a mineral phase, which we will cover here. And another would be a kinetically limited reaction that takes place in the aqueous phase, which we will address in a later module. So, as stated, Freak-C comes with a built-in basic language interpreter. The scripting language contains a number of features, each of which is documented internally in Freak-C's help system. I've shown some screenshots of this here. The objective for each rate law script is the same: express the rate of change of the amount of the reactant as a function of the chemical state of the system. In other words, as an ordinary differential equation. The Freak-C.dat database comes preloaded with a few rate law expressions written in the scripting language. This is a good place to start using or modifying one of these, or by using one of these rate law scripts as a template. So in terms of actually setting up a kinetic simulation, there are two parts. There is a rates keyword block and a kinetics keyword block. The rate law itself is expressed under the rates keyword block. For this problem, I borrowed the pyrite dissolution relationship already supplied with Freak-C.dat. Note that the dissolution rate here depends on the specific surface area of pyrite, the dissolved oxygen content of the solution, and the pH. The initial amount of the kinetic reactant and the time-stepping constraints for the simulation are listed under the kinetics rate law block. Here, M refers to the initial mass of the kinetic phase pyrite in moles. So here are the time-dependent simulation results for two different scenarios I ran using this particular rate law. The first one on the left is for pyrite crystals that are modeled as perfect cubes that are 0.15 millimeters on a side. At a concentration of 3% of the rock by weight, you can work out the specific surface area for this. You can see that the pH drops to a rather acidic condition just before 60 days as calcite, which buffers the pH in this model, is exhausted. All of that calcite dissolution frees up a lot of calcium. When combined with the sulfate formed when pyrite is oxidized, gypsum or calcium sulfate is precipitated. At the same time, the ferric iron sent into solution from pyrite oxidation forms a hydroxide precipitate. This precipitate itself begins to slowly dissolve after 60 days as conditions become ever more acidic. The simulation results shown on the right are for a model with pyrite consisting of 0.3 millimeter cubes on a side, and thus offering a lower specific surface area. The same sorts of reactions occur, but they are delayed to a later time owing to the slower rate of pyrite oxidation. So, after all of this, I propose a challenge exercise. Try modifying the granite weathering advective transport input file for the first example in this module to treat both potassium feldspar and albite as kinetic reactants based on the rate law template supplied under Freak-C.dat. The second part of this is try to get the simulation to work. Are there any particular challenges? This is something we can discuss later.